So I'm very happy to be here, and I'm even happier to be here as a visitor for the semester. It's fantastic. So I hope that this is a high-level talk. You stop me and ask me questions if it's not understandable. So I'm going to talk about sparse matrices and two vignettes on a theme, the theme of sparse matrices. And in one setting, the sparse matrices, we try and design them. And in another setting, we try and compute quantities that are sparse matrices. So they're going to play two different roles in two very different settings. Okay, so the first setting, here's a summary. In the first setting, right, we want to design a sparse matrix for compressive sensing. A sparse matrix is one which doesn't have very many non-zero entries in it. And then in another setting, we want to try and repair a distance matrix and do so sparsely or parsimoniously. So one is more of a design question, but design plus algorithm. And another one is much more of a geometric plus algorithms question. OK, so that's the setup. I'm going to start first with the compressed sensing theme, and then I will talk about the metric repair theme. OK, so in the first setting, I said we have a design plus an algorithm problem. And so here's, hopefully fairly cleanly, a setting for sparse signal recovery. So I have a signal of length n that I do not know. I'm going to assume that it's roughly k-sparse, i.e. it has k non-zero entries in it. If you want to be a little bit more technical, let me assume that if I take the absolute values of all of the entries, then k of them are really big, and all the other n minus k of them are really small. Really small might even be 0. The important point here is that it's the absolute value. And I will always forget that and just say the k biggest. And you'll go, oh, yeah, an absolute value. Yeah, we're good. OK, so this is a signal of length n. It's roughly k sparse. And we want to design a matrix, this lovely speckled thing. We want to design a matrix, and we're going to use this matrix to take observations or measurements of this great big long vector. So we're going to design a short, fat matrix so that we don't take too many measurements. And how many measurements would we like to take? Well, roughly k log n of them. K, because we're looking for k pieces of information in a vector of length n. Here is a rough argument for why k log n. This is not a correct technical argument, but it works really well. So if I have a k-sparse vector of length n, how many bits do I need to encode the positions of the k non-zero entries? I'll let you do the calculation, and then you'll see why k log n measurements should be about right. OK, so designing a matrix to take observations of a signal would be one thing. We got to do something with those measurements, or I should say we want to do something with those measurements. In particular, we would like to recover information about the signal. Remember I said you don't have access to this signal? You can take linear measurements of it, but you don't get access to it. OK, so here is the design problem. Assume that the vector that you're trying to measure is k-sparse. It has low complexity. And you want to construct or design or build a matrix A that has m rows and n columns, m as small as possible. Remember the rough back of the envelope calculation, k log n, actually k log n over k. You want to do that so that given measurements of any roughly k-sparse signal x, we can quickly recover, i.e. we can also come up with an algorithm that has knowledge of A. We can quickly recover information about x from measurements AX. OK, what kind of information are we going to recover? What kind of error metric? What kind of output are we interested in? Well, we'd like our estimate of the vector x to be close in some LP norm. I'm not going to specify p quite yet. How close? We would like this error to be no more than some constant times the error of the best k-term representation of x in the LQ norm. That's what that means. Take the minimum over all y that are k-sparse. Okay. I'll let you guys do a little thought experiment. What is the best y that is exactly k-sparse, that minimizes the LQ distance from x? May I suggest you consider the k largest entries in absolute value of x? That's a good one. Okay, which p and which q? Well, that gets a little technical. Okay, so we might discuss some of that. You can for certain values of p and q, or certain values of p. If p equals 2, so you want the best error in L2, blah, 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 then under certain rather technical conditions, if you want this to work for any signal x, one matrix for all signals, then m is roughly the size of n. There's a lower bound. Okay, if you do some wiggling and adjust what it is you're asking for, and you say, maybe I would really like A to be drawn from some specified random distribution, and I'm going to draw A and then measure one single x, and then ask to get recovery with high probability over the randomness in the matrix, and do this, like roughly 1a per vector x, then you can get away with m small and p equals q equals 2. So, if you want a really, really strong guarantee and you want L2, then there are lower bounds, and m cannot be very small. Okay, if you want for all guarantees and you want L1, then you can make m quite small, and I'm actually that's the case I'm going to discuss. The more standard case is p equals 2 and q equals 1. The geometric intuition you should have here is the relative sizes of the L1 and the L2 balls in high dimensions. Okay, one of them is much bigger than the other. That's an awful lot of vectors to try and recover. Okay, that's the intuition. Okay. All right, so Yaim and I had a little bit of discussion about these p's and q's. There are more parameters in here that we could worry about, like the number of measurements, right? We had some discussion about how small can m really be, when m be as big as n. We didn't talk about the recovery time of the algorithm. That's really important. In fact, actually, to me, I spent quite a while trying to come up with very, very fast algorithms, and just embedded in this design problem is this question, how quickly recover? Well, how quickly is quickly? Okay, so can you come up with an algorithm that recovers only, roughly speaking, the k largest entries in x? Yeah, that would meet the criteria for this kind of error. Can you find the k largest entries in x in time roughly proportional to k? Or in time roughly proportional to the number of measurements that you take, so something like k log n. Okay, or, God forbid, do you have to do this in time polynomial in n, the length of the vector x? In other words, do you have to take as much time as it would be to potentially compute every single entry of x to find the biggest entries, the k biggest entries in x? Okay, so recovery time really matters. The difference between n and log n is huge, I think, exponentially. Okay, so we talked about approximation guarantees. P and Q, and does P equal Q, and under what conditions can you get P and Q equals to 2, etc. I hinted at an answer to this question lies in whether or not you want to guarantee the existence of one matrix, or whether you want to play a different sort of game where you specify a distribution over matrices, you draw the vector, you then draw the matrix, you take the measurements. So, exactly where the randomness enters into this problem matters. And is it one matrix? Is it simply a distribution over matrices? Or even worse, do you have a distribution over signals? Okay. As soon as I tell you one matrix, and there might be potentially an existential proof, it might be interesting to ask, could you come up with an explicit construction of this matrix? So could you design a matrix and then construct it explicitly? Could you construct it explicitly in polynomial time? That's also an interesting question. These are all fine and good mathematical and algorithmic questions, but they're really not very practical. Because whenever you want to build a system, or you might want to build a system, I guess I should say people have built systems that are based on these ideas, the world is far from perfect, and you need to be able to address measurement noise in your experiment. So that's the idea that this computation is not simply a clean matrix vector product, but it might be the result of some physical system, some physical measurement. And physical systems are never perfect. And so instead of getting simply this beautiful matrix vector product, you also have noise added in here of a certain variety. Okay. All right, so these are all the various parameters or things one might worry about in designing a matrix and an algorithm for recovering a sparse signal, whether you're doing it sort of computationally, whether digitally, whether you're doing it physically, or whether you're doing this as a mathematical problem. Okay, so where might people have actually come up with these kinds of problems in various, either digital, real, physical, or mathematical applications? So a digital application arose in a field of algorithms called data stream algorithms, where the vector x was recording the number of items that appeared in a stream of updates, the number of items with index I in a stream of updates. And so in particular, like, I used to work for the phone company, and we used to process call detail records, and there would be like 350,000 350 million, a lot, every day. And you'd want to know, how long was a phone call, from A to B, i.e. with index I, on this particular day. And so the vector x might be encoding the length of phone calls from all possible phone numbers in the US, right? This is another example of this, okay? And so, that might be kind of a great big long vector to maintain. Digitally, you might not have enough memory to do that. But remember, a times x is a much smaller vector. In fact, it's exponentially shorter than the original vector x, and so that requires much less memory. And in this digital setting, the matrix vector product a times x really is linear. There's no noise. There's no measurement noise. And so it's very easy, if I change x, to change the measurements a times x, because matrix vector multiplication is linear. So whenever I see an increment to xi, it's easy for me to adjust my measurements a of xi. And then you ask, can I recover an approximation to x? In particular, can I recover the heavy hitters in x, or the heavy hitters in the, who's making the longest phone calls every day on a telephone network? Okay, so that's a digital application. I'm going to talk about a physical application. So using ideas very similar to this a times x setting, there were several groups of electrical engineers and designers in the last 10, 15 years who built a couple of different kinds of physical systems using this idea of taking a reduced number of physical measurements in a random way. And so one of the famous ones was called the single pixel camera. And the measurement matrix that was random was an array of mirrors that you could control and that would flip sort of at random, and they would add up the photons, hitting these mirrors, and you'd collect a sum of these values in a CCD array. And right, there we go, low-cost, fast-sensitive optical detection. And the idea was to try and reconstruct images using just a few random measurements of light. People also built analog to digital converters. So in a slightly different setting, if you can take random samples of a signal, then of a signal that doesn't have very many frequencies in it, then you can quickly come up with the spectral information in the signal, and so you can then digitize that. So people built analog to digital converters using ideas sort of similar to this. And then finally, okay, so this is digital, physical, and then sort of mathematical. You can view this problem as an instance of error-correcting codes, where the error vector of your received code word is x. A times x is your syndrome, and you want to figure out where are the errors in my received code word so that I can decode. So this is kind of a nice mathematical example of sparse signal recovery. Okay, so these are applications. Let's talk about how people went about solving mainly these and these. For me to actually talk about electrical engineering is A, beyond this talk, and B, doesn't fit into this vignette nicely. Okay, so let's talk about the digital applications and then sort of the mathematical applications. And in the last 15 years or so, there were two main approaches to solving the sparse signal recovery problem. One of them I will call geometric, and the other one I'll call combinatorial. And the geometric method, the geometric ideas were beautiful mathematical ideas that really started with the idea of, can I characterize the kinds of matrices which are useful in sparse signal recovery using a certain kind of algorithmic approach, which I will call geometric. Okay, and so basically the recovery matrices are essentially dense. They are, like Gaussian or sub-Gaussian random matrices, or they're not structured random submatrices of a Fourier matrix of a DFT. And so, they're dense. Many of them required or seem to require an awful lot of randomness. So these Gaussian random matrices were, all the entries are IID Gaussians. And the recovery algorithms were all of the form of convex optimization. So return the vector with smallest L1 norm that is consistent with the measurements that you collect. And you've got a uniform guarantee. This is a bit technical. The guarantee that there was one matrix A that would work for all vectors X. And the proof was essentially existential. Okay, then there were these combinatorial methods that were frankly kind of a mess. They were sort of crafted, I will say, inelegantly. It's okay, I worked on a bunch of them, so I will say it was inelegant. They were kind of ad hoc. They sort of began with the idea of, I need to design a matrix. Like, how do I, I have to write code to handle data streams. How do I do that? And so the matrices that were built were typically sparse. In particular, if you think back to the data stream applications where I reminded you that linear algebra is linear, and that a times xi is a linear procedure. In order to update your vector of measurements, when you see an increment to index I and only I, all you have to do is to pull out the ith column of A and add that to your measurements. Decorate it, weight it by however many things are in xi. Okay, but that means that you need access to A, to the columns of A. In other words, that means that you need to either generate them quickly or store them efficiently. Okay, I assure you that storing random matrices is not efficient. So you need a structured, sparse, possibly random way of storing, or a quick explicit construction for these matrices in order to get these like super fast digital applications to really work. And then the algorithms were incredibly fast. They were also kind of inelegant. They were greedy algorithms, and they worked on, they took time roughly proportional to the number of measurements. So, i.e., exponentially faster than anything that was based on linear programming. In particular, these algorithms were not producing a vector x hat that was as long as the original vector x. They were producing the k largest items, or a good approximation to the k largest items in the vector x, and the rest of the vector, who cares? The recovery guarantee is only as good as the first k items. Why bother computing all the rest of the stuff? Okay, so that was the idea. And at first they were this technical per instance guarantee, and then later we could get more uniform guarantees like this. Okay, so they seemed like very different kinds of methods. This was elegant, this was beautiful mathematics, there's all kinds of geometry in here, and this was, sort of seat of the pants constructions that just sort of worked. Okay, and so at some point we wondered, is there anything that's similar between these two approaches? They have the same sorts of guarantees, and yet they're going after very different objects, and they have very different algorithms. How do you reconcile these two? And in particular, would it be possible to unify these techniques? Would it be possible to understand the geometry of these very sparse combinatorial constructions? And in particular, could you take these sparse matrices that were very structured, and could you just apply a geometric decoding algorithm to them? Okay, so in other words, what do the combinatorial and geometric approaches share, and what makes them both work? So we spent a while working on these. The answer happened to be expander graphs. So I'm telling you the answer ahead of time. It took a while to work all of this out. Telling the story, not how it happened, but telling you the story in an exciting way is better than telling you, how much we sort of stumbled around until we hit upon this. Okay, so we hit upon this. Essentially, what were these sparse random matrices? They were the adjacency matrices of bipartite graphs, and in particular, bipartite expander graphs. So what kind of bipartite expander graphs? They were the adjacency matrices of d-regular k epsilon expander graphs. So what is that? Well, bipartite. So you've got a left side and a right side. Think of the left side as being length n, the length of the signal.
This is what you were using.
Yes.
You were using ones that you made up.
Okay, so
before you knew expanders, you were just
random.
You were just choosing.
The random is actually too much randomness, and if you don't want a uniform guarantee, then you can use like 4-wise independent random variables, and those will just be random code words out of some nice linear code. But it doesn't give you quite the power of an expander. On the other hand, they're much more efficient. Okay, this is the clean answer. The really dirty answer is BCH codes of a certain type. Okay, so right, x is of length n, y is of length m. That's the left side. This is the right side. This is the signal. These are the measurements. And what is a d-regular k epsilon expander graph? So every outgoing node here has degree d. I think that's the setting. Either that or every node over here has degree d. I forget which. And for any subset of size at most k on the left, the neighbor set of vertices on the right is almost d times the size of S, and you fail to have perfect expansion by this parameter epsilon. Okay, so ignoring this part, this is easy to achieve if M is d times n. If M is huge, it's very easy to construct a bipartite expander that meets these criteria. What's hard is to make M small. So the tension here is in the degree and in the number of vertices on the right. And the trade-off is in n, k, and epsilon. And what do you know? There are probabilistic constructions with degree log n over epsilon. And the number of measurements, look at this, k log n over k. And then it's epsilon squared. Okay, probabilistic constructions meaning in every entry is 0 or 1 with the appropriate probability so that you get the right degree. I can't work this out in my head. Okay, there is a deterministic construction. This is probably not the best deterministic construction as of 2019, but it was the best when I wrote the paper. And the gap between deterministic construction and probabilistic construction is a long-standing open problem in combinatorics and theoretical computer science. Okay, so it turns out that adjacency matrices of this type are the right sparse matrices that you should use for sparse signal recovery. And in case you want to know, like, exactly how does that work, so here's the bipartite graph, here's the adjacency matrix, and then an even larger version, here's the measurement matrix. Sure enough, it's fairly sparse. Kind of interesting is to think that there were people who were building optical systems who were using coded apertures, which is coded, C-O-D-E-D, not coated, coded apertures. In other words, they were placing filters that looked like this in front of beams and then collecting information about the light. And that's what these things looked like. Which is kind of neat. I didn't know that they were doing this, and they didn't know that I was doing this kind of thing. And they would show me these optical systems. I was, oh, that's fantastic. It looks just like my MATLAB pictures. Okay, so that's the picture. Okay, so far all I've told you about is combinatorics. I've told you about combinatorial objects. I haven't told you what geometric properties these things enjoy. So it turns out that these things enjoy very nice geometrical properties. Again, we didn't know this until we sort of started thinking about this. So the geometrical methods began or were set up with a geometric characterization of these dense random matrices. And that was that these dense random matrices satisfied an RIP condition, a restricted isometry property. And restricted isometry property of order k and parameter delta. And basically, the interpretation is that on k-sparse vectors, these dense random matrices were near isometries. So on any k-sparse vector, the L2 norm of the vector was roughly equivalent to the L2 norm of the original vector. Okay, it turns out for one can and replace 2 with a generic p, and in particular make p equals 1, and ask whether or not a matrix is a near isometry in L1 sense. So will a measurement matrix essentially preserve the L1 norm of any k-sparse vector? And you could call that RIP1. You could stick in any p, call this RIP-P. Okay, but making p equals 1 is useful. In particular, making RIP1 gives you essentially an exact characterization of these bipartite expanders. So the theorem is, roughly speaking, that a matrix will satisfy RIP P for a certain range of P if and only if you have an expander, okay, which is a lovely marriage, I think, of geometry and combinatorics, and not a known characterization of expanders, in terms of spectral properties of the matrix. And so the theorem is that if you have a k epsilon degree d bipartite expander, then it satisfies an RIP1 condition. And in fact, actually, you can bump it up a little bit to 1 + 1 over log n. Proving that this is true for p equals 1 is easy. One direction is easy. One direction is not so hard. Not that hard. Fattening up p a little bit gets a little trickier. It's also not clear to me that this is important. It's true, but I don't know how important it is. Okay, the other direction is also very important, and that is that if you have an RIP1 matrix that you know is binary and sparse, then it must be a k epsilon expander. So RIP1 if and only if an expander. And you get, you can understand the relationships amongst the parameters. Okay? All right, well, that's fantastic, but we need an algorithm. Okay, so it's one thing to take measurements, but it's another thing to come up with an algorithm. And for the expander matrices, they don't enjoy as much structure as the ones that we created by hand. We kind of built and stacked this code on top of that code, et cetera. But they do, so they're not so amenable to super fast, clever, ugly algorithms. They are amenable to lovely geometric L1 minimization type algorithms. And there are several theorems in a sequence that show that if you have a bipartite expander, then LP decoding will work to do signal recovery in the L1 guarantees. So P equals Q equals 1. So yes, okay, this is the correct statement of the theorem. It says that if you have two vectors that have the same measurements, and one of them has L1 norm smaller than the L1 norm of what you've measured, i.e. it is the minimum L1, the minimum minimum L1 norm vector, then it is within some constant times the L1 error of the best k-term representation of the original signal x, and here is 1, and here is 1, and the constant is a function of epsilon, and actually it's a function of it's a function of epsilon. Here is the function, and this epsilon is related to the expansion factor. Okay, so this theorem guarantees that linear programming recovers a good sparse approximation. Linear programming is a lovely geometric approach to solving these problems. So we've taken a combinatorial object, employed a geometric algorithm, and everything works nicely. You can also show this as robust to noisy measurements. Okay, how you prove this is via an L1 uncertainty principle, which is essentially the same kind of way that you prove the RIP2 results. And the important result in here is basically that vectors in the null space of A are flat in some L1 sense. So that's essentially what this says. Okay. I don't want to go too much into these theorems. I like the L1 uncertainty principle and the L1 null space condition. It has exact analogs in the L2 setting. Okay. Now, you might ask, how much do RIP1 matrices look like RIP2 matrices? And I will say they look like one another only when you have lots and lots of rows. When you have a small number of rows, they look very much not like one another. And so someone showed in 2007 that if you have a binary sparse matrix which satisfies RIP2, then it must have a fair number of rows, like k squared rows. So it's got to be pretty tall. This k squared being taller than k log n for the appropriate range of k. OK. You can also do the following thought experiment and take a Gaussian random matrix with k log n over k rows appropriately scaled and hit it with two different vectors that have the same L1 norms. And you'll see that the L1 norms of the measurements gx and gy are quite far apart from one another. So it's sort of a two-way comparison of RIP1 versus RIP2. OK, so they're quite different from one another unless you have a fair number of rows. Maybe you don't necessarily want m as small as possible. Maybe you want m a little bit bigger to tolerate other stuff, in which case, you're kind of in this setting. OK, so Peter walked out. Now I'm going to tell you about a real application where we actually use this, and we threw most of this mathematical analysis out the window. Because it's a real application. And none of this math is going to work in practice. OK, so we threw it out the window. OK, so here is the application. So there were several computational biologists that we were talking to. And they said, these sparse matrices, they look like pooling designs for testing for rare alleles or pooling designs for looking for, carriers for various kinds of diseases, for testing libraries of drug compounds. People who do like next generation sequencing, they actually do this kind of pooling with these sparse matrices. We would like to talk to you about doing these pooling designs. We have this pooling design that we've called the STD, which is funny if you know the origin of group testing, which was for syphilis testing of draftees in World War II. The STD was for shifted transversal design, and not for syphilis. And the patterns looked like this. They had some formula for doing this. And, I was sitting next to a friend of mine who's an expert in algorithmic coding theory, and he says, "Psst, Anna, I think that's just a concatenated Reed-Solomon code." I said, "Yeah, I think so." So we went and looked at the formulas. Yeah, sure enough. So, what had these biologists discovered? They had rediscovered graphs of low-degree polynomials over finite fields. And that was how they had constructed their sparse binary measurement matrices. These are far from, like optimal expanders, but they do have some very nice properties. In particular, so they have very nice properties. You can read off what all the polynomials are. You can design these explicitly. You can store them efficiently. They have other really nice properties. So the biologists were very concerned that the number of ones in each row be exactly the same. They were also very concerned about stacking together more samples. So we're going to collect this kind of sample, from this population. We're going to collect more samples from this population, and we'd like to test these guys and test these guys, and then somehow pool them all together. Test these two sets of samples together. And they would describe this as, we want this design to be modular. It's like, oh, you want a different coset. It was eventually what we figured out. Oh, you want, you just increase the degrees of the polynomials and you get a different coset. Then they wanted to program this thing. So, this is fantastic. These are, arithmetic over finite fields. This is very easy for us to do. Much easier than, designing this thing at random. They were very happy with this. Although explaining to them how to do arithmetic over a finite field was horrible. So they designed this iPad application. I kid you not, they had a grad student, or maybe a lab tech, doing the pipetting and the pooling, by hand, in order to say, this compound goes in this well, this one, this one, this one, this one. Talk about tedious. It's much better to be a math grad student. OK, so they actually did this. It was really cool. It's also kind of depressing, all this beautiful mathematics, and really what they want are low-degree polynomials over finite fields. Okay, fine. It works quite well for exactly what the biologists want, I will say. Okay, so it does. It works quite well. They actually don't want m as small as possible. They want a bunch of robustness, and they want sort of modularity, and they want kind of explainability. And somehow random constructions were not satisfying to them. They also liked the fact that you would get these patterns in these STDs because you could do some kind of eyeball check to see whether or not the pooling had been done correctly, which was kind of neat. Okay, so this was one vignette, sparse matrices in signal recovery, and the whole point was to design a sparse matrix and to have that work with algorithms and geometry, and in the end to tell a story about an actual application. So I'm going to switch gears to a completely different story and talk to you about sparse matrices in a much more recent problem in sparse metric repair. And here I am not trying to design a sparse matrix. I'm just trying to find a sparse matrix that is sort of a good solution to a particular problem. Okay, so here is the setting of the problem. So I have, so in many data applications, this is a special year on the theoretical foundations of machine learning, and many machine learning tasks, one is given a matrix of distances or similarities, or one has a data set and computes a matrix of pairwise distances amongst all the data points. And as I have explained to you in many different settings, when you have a real application, your data is often corrupted. It's noisy, it's garbagey, nothing works quite right, you have missing values, and how accurate, how faithful these distances are, how uncorrupted these distances are, is often not really asked when running these machine learning algorithms. And so in particular, they're not often assessed for whether or not the distances satisfy a metric. So a metric, the entries, the distance from one point to itself should be 0. You should have a triangle inequality be satisfied. The matrix of distances should be symmetric. The entries should be non-negative. The one that I really care about is the system of inequalities, the triangle inequalities. So I'm going to rewrite I'm going to take this matrix D. I'm going to stretch it out. Ignore duplicates. I'm going to stretch it out in a great big long vector. That's what this vec means. So stretch out all the distances. And I'm going to encode the triangle inequality in this matrix M. This matrix M is tall and thin. It is also a sparse matrix, a bunch of zeros. Each row has 2 1s and 1 negative 1. And I say that this matrix D, the set of distances satisfies a metric if M times the vectorized form of D is element-wise greater than or equal to 0. Somebody may ask me, how do you ensure the non-negativity? Stick in the identity into M. Be done with it. Okay, the important point is that all the triangle inequalities be satisfied. Okay, so in lots of machine learning algorithms, and in fact, even in more theoretical, like graph algorithms, these algorithms can be run more successfully, or I should say there are guarantees for when your distances satisfy a metric. There are approximation algorithms for when your distances satisfy a metric that just do not hold if you do not have a metric. So TSP is one of them. There are applications in computer vision where it's very handy to know that the distances adhere to a metric. And it also comes up in computational biology problems. So given similarity or distance data, how do we ensure that it's a metric? Right? Before we run any of these fantastic algorithms, how do we ensure that we even have a metric? Okay, so formally, here's my problem statement for metric repair. So suppose I'm given a corrupted metric d prime, i.e. some triangle inequality is broken. Find a perturbation that repairs the metric. So find some perturbation p such that input plus perturbation gives you a proper metric. Okay, that seems like a reasonable problem. Okay, all right, here d is the corruption of the metric, p is the repair. Okay, so that seems like a reasonable problem. Yeah?
Don't you want the perturbation to be small?
Aha, yes.
You just bump the distances to infinity.
Yeah, okay, so I'm getting to that. Okay, so there are a bunch of different ways you could set this up. You could how small is small, in what norm, etc. So this problem was originally called the metric nearness problem by Brickell et al. About 2007. And they said, give me the nearest metric that minimizes the L2 norm, or the Frobenius norm. So small in L2 sense. Okay, so in other words, project onto the subspace of metrics. Okay, you could also ask to project onto the cone of Euclidean distance matrices, or Euclidean matrices. And so again, this is the closest Euclidean metric, closest in L2 sense. This is what multidimensional scaling is. It's used extensively in the psychometric literature. It goes back even further than 2007. Multidimensional scaling is still used. It's a fantastic algorithm. There was also a randomized.
It's not a cone unless you square the distances.
Yeah. You notice I said Euclidean distance matrices, Euclidean matrices. Yes, there's quite a difference. Yes. Right, I'm sweeping that detail under the rug. Okay, so there is a randomized algorithm for R3, which is kind of cute. It goes back to the late 90s. You could also say, what Cauchy, the sort of rigidity theory that Cauchy was looking at in the 1800s is sort of related to, how many distances can I change and still preserve various properties of polygons. The problem with all of these methods is that they perturb most of the distances. And I would like to take a more optimistic approach and assume that most of the distances that you're given are correct. It's just that a few of them are corrupted, and I would like to repair as few of them as possible. So I would like to minimize the L0 norm of the perturbation, i.e., I would like to design a sparse matrix such that the corrupted distances plus the sparse matrix will satisfy all the triangle inequalities. Okay, so having sat through a lecture on compressive sensing, having followed 15 years worth of literature, you might be tempted to change this problem to that problem and do the L1, the convex relaxation of this problem, and minimize the L1 norm of the perturbation that corrects the distances. And I would say do not do that. It's very tempting. It's very successful in many other applications, but don't do that. So you implement it and test it. The naive solution, an implementation that solves this sort of naive setup does not give the sparsest solutions in general. So you can fix this up, if you make it slightly fancier and you do like iteratively reweighted L1, something much fancier will give you something better in practice, but it's kind of unsatisfying. And in particular, all of that intuition from 15 years of stuff, not so helpful. So M here is overdetermined. It's tall and thin. It's not like these short, fat, random or nearly random matrices. It's not particularly incoherent. These columns are far from random. It's kind of a completely different problem. Okay, so you might also be a little concerned about the number of constraints in this problem if you were to do this with convex optimization. And, there are n cubed constraints from each triangle inequality. Solving these large LPs is expensive. I don't think that simply solving an LP sort of gives you an idea of the combinatorial nature of the problem. It just doesn't give you much insight. It's kind of a machine. So maybe we could efficiently detect whether or not the input matrix is a metric. Might it be possible to even find the broken triangles quickly? You might be tempted. Are you tempted? Please do not be. It's not likely to happen. So probably not. So we're kind of stuck with these number of constraints. So Williams and Williams in 2010 said all of the following problems either all have truly subcubic algorithms or none of them do. So in the middle of this list is checking whether or not a given matrix defines a metric. What's cute is that this all pairs shortest path problem should give us a clue as to the combinatorial nature of part of this problem. Okay, so I'm just going to totally punt on these n cubed number of constraints, and whatever work I do on this problem or variations of this problem will have to handle in some sensible way all of these inequality constraints. Okay, or I'm just going to have to deal with a cubic time algorithm. Okay, so let's think. Am I supposed to end at 250 or 3? Oh, okay, excellent. All right. Okay, well, I may go faster through this. Okay, so all pair shortest path. Oh, that's a very well-studied problem, and there are all kinds of great algorithms for all pair shortest path. They are even taught in undergraduate algorithms classes. Let's keep that in the back of our mind, and let's separate these metric repair problems into different cases. And let's see if we can understand like what's hard in one case, what might be easy in another case, like fundamental differences between these cases. So the first one we called, I actually think Brickell called this, decrease only metric repair. And that is I'm going to constrain my perturbations to be negative or 0 only. All I can do is decrease or leave alone the length of sort of a distorted leg of a triangle. So, i.e. d prime was perturbed by positive perturbations. So I have this triangle, this distorted triangle 1, 2, 7, and I've bowed out 7, that leg, to say that's the one that's too long, and you should shrink it to 3. Do a quick check that 3 is the shortest path between these two vertices through those two legs. Okay? Then there's another variant of this problem where I'm going to constrain my perturbations to be non-negative, i.e. all I'm allowed to do is increase or leave alone the length of the legs of triangles. So here I've got 1 bowed in to say that this is the one that's too short and it should be increased. So change it to 5 and you get a proper triangle. Okay, I would observe that a sparse solution in this setting may not be the same as a sparse solution in this setting, and vice versa. It's the same triangle, 1, 2, 7, but I get 2 quite different fixes. So it suggests that we should look at repairs. It suggests that we should look at these 2 cases separately. They are really very different. There's also a general case where you don't place any restrictions on p. You could be positive, you could be negative, you could shrink, expand, etc. But this one I want to keep separate from these 2 cases. Okay? So the answer to how to solve the decrease-only metric repair is an undergraduate algorithm. It is one that could be taught to undergrads. There is a polynomial time algorithm for solving decrease-only metric repair. It gives the sparsest solution. It gives the best, it gives the smallest solution in any LP norm. It does not involve running some giant LP. It just involves running Floyd-Warshall. So this slide is saying, notice that 3 is the length of the shortest path from I to j through k. Okay, and there is a theorem that says that if dA is the solution that you obtain after running the Floyd-Warshall algorithm on the complete graph with edges whose weights are equal to the input distances, then the perturbation dA minus d is the sparsest possible decrease-only solution. And in fact, it is the solution that minimizes the L1 norm, but it also minimizes any LP norm. Okay. Then, of course, it's a cubic. Most likely, it's a cubic algorithm. Okay, this is lovely. I think it's fantastic. It's kind of simple. In fact, actually, it's very simple. It makes it not so fantastic. It's so simple. The other case is much harder. In particular, it's hard in a very technical sense. Okay, so the increase-only metric repairs problem is hard. It's NP hard. Sorry, it's also NP complete. Okay, so why might it be hard? Okay, so if I have a broken triangle, this leg is greater than the sum of these two legs, and all I can do is increase the leg of a triangle. So which one of these should I pick? Don't know. Okay, so that's the problem. That's the sort of combinatorial explosion that should give you some intuition as to why this version of the problem might be hard. Okay, I'm also going to bash L1 minimization and say, look, even if you were to throw L1 minimization at this problem, you get lots of possible solutions, but very few sparse ones. And in fact, there are lots of them that have total L1 norm 4, and it's really hard to distinguish amongst them. So this is not a good algorithmic approach. Right, so yes?
If you randomly perturb all the distances before doing the L1 projection, my metric is kind of stayed almost the same in terms of distances, and then you do an L1 projection. Now you might hope you've broken all of these symmetries and actually get a sparse solution.
Yeah, so we haven't done that experiment. We did do a bunch of experiments on random graphs and randomly placed points with randomly jittered distances, and then run naive L1 minimization and iteratively reweighted. So I don't know if I can't think immediately off the top of my head whether our experiments would say, yeah, what you just suggested actually doesn't work. Right now, randomized algorithms for increase-only metric repair we do not have. We have approximation algorithms. We don't have randomized approximation algorithms. We also, in a very early paper, had a bunch of experiments on various kinds of random instances, and I'm not really sure. I'm not sure what to make of these experiments in connection with the approximation algorithms or the hardness results. They're kind of like apples and oranges right now. So for the sake of time, I'm just going to say we have extended this metric repair problem to more general graph metric repair. So instead of constructing the complete graph on n data points with the weights being the distances, and suppose that the graph is not kn, but is some input graph, and it's capturing the relationships amongst different data points. Like this data point is not at all connected to that data point, so do not put an edge between them. And then the analog of broken triangles is broken cycles. And so we have come up with, so there's a hardness result for the general version of this metric repair, graph metric repair. It says if you allow any positive increase in the weights, even a single number, the problem becomes NP complete. So it's not simply, allowing any allowing all possible positive numbers, but any single positive value sort of breaks the easiness of the problem. We have approximation algorithms for increase-only metric repair. The approximation factors are parameterized by a couple of different graph quantities. One of them, the length of the longest broken cycle. One of them, the size of the most broken cycle. We've also used this idea for sort of data imputation, but really more like, suppose your distances are corrupted because you have missing values in your data. Instead of filling in values, repair the distances, and then run, sort of downstream machine learning algorithms like manifold embedding. Okay, so I'm going to end here and say much of these ideas were inspired by listening to computational biologists talk about single-cell RNA sequencing data where you have sparse matrices with very, very few gene expression counts for a bunch of different cells, and the biologists want to know very much things about the geometry of cells. And how in the world can you do that with very sparse matrices and missing data? Okay, so thank you.
Thank you very much.